My name is Josh, and I'm going to be walking you through problem number 3 on the 2013 AP test. Alright, so this problem starts off with question A. Which is the limiting reactant in the 4 trials? Hydrochloric acid or magnesium oxide? And tells you to justify your answer. So to do this problem, you have to use this chart, which I've recreated here, and you probably have in front of you, because since you're working on the problem now. So, for this problem, we're just going to use 0.50 grams because that is the largest amount of magnesium oxide used. And first thing we're going to have to do is write down this balanced equation. So MgO plus 2H plus gives you magnesium 2 plus and water. Then from this balanced equation, you can use stoichiometry to determine how many moles of product each thing in this chart creates, each reactant creates. So, 100 milliliters of HCl will create, this is 1 gram per mole and 1 mole of hydrogen, but we need 2 moles of hydrogen to create 1 mole of H2O, so divide it by 2. Creates 0.50 moles of water, as you can see by that work. Now we're going to use magnesium oxide, which I'm guessing you're already thinking is the limiting reactant. So we have 0.5 grams magnesium oxide, and then after that we go 1 mole of magnesium oxide, and the molar mass of magnesium oxide is about 42.98 grams per mole, and we need only 1 mole of magnesium to create this Mg2+, so we don't have to worry about that. 1 mole Mg2+, 1 mole MgO. So that will produce about 0.0125 moles of Mg2+ and 0.0125 moles of H2O. So because MgO produces so much less product than HCl, it is the limiting reactant. Because we have less MgO and produces less moles of the product, the reaction is dependent on how much MgO we have as opposed to how much hydrogen or hydrochloric acid we have. All right, now on to question number 2, which is B. Now question B is where this chart's going to come in real handy. So, question B says the data in one of these trials is inconsistent with the data in the other 3 trials. Identify the trial with the inconsistent data and draw a line through the data from that trial in the table above. Explain how you identified the inconsistent data. So, the first thing we have to look at is the final temperatures and initial temperatures of all the trials. Trial 1 has an initial temperature of 25.5 Celsius, while it has a final temperature of 26.5 degrees Celsius. That's a total change, or delta T, of 1. Trial number 2 has 25.0 degrees Celsius initial and 29.1 degrees Celsius final. That's a delta T of about 4. Trial number 3 has a initial temperature of 26.0 degrees Celsius and a final temperature of 28.1 degrees Celsius. That's a delta T of about 2. And trial number 4 has an initial of 24.1 and a final of 28.1. That's a delta T of 4. So, from looking at these problems, you can probably determine which one is the incorrect data just by looking at it. For instance, trial number 1 here uses 0.25 grams of magnesium oxide, and trial number 3 also uses 0.25 grams of magnesium oxide. However, we can determine which one is incorrect by looking at the trials that use 0.5 grams of magnesium oxide. Because we're just doubling the mass, you'd expect it to have the same result in the delta T because it's a scalar quantity. So if the delta T for 0.50 grams of magnesium oxide is 4, we'd expect the delta T for 0.25 grams of magnesium oxide to be 2, not 1. So this trial is invalid with the current reasoning that we are having here. And that is because this quantity is only 1/2 of that quantity. So this delta T should be 1/2 of that delta T, not 1/4 of that delta T. So trial 1 is inconsistent with the data based off of the quantities of MgO added and the difference between the final and initial temperatures. All right. Then part C and D, we're assuming that we're going to use the data from one of the 3 trials that work, so trials 2, 3, or 4. And we're going to assume the calorimeter has a negligible heat capacity, and the specific heat content of the calorimeter is 4.18 joules per grams degrees Celsius. And we're going to assume that the density of hydrochloric acid is 1.0 grams per milliliter. That's a lot of words. Basically what that's saying is that you can just use your formulas without having to adjust for anything. So, for problem number C here, we have calculate the magnitude of Q, the thermal energy change, when the MgO added to the 1.0 milliliter of hydrochloric acid, and include units with your answer. So here you're going to use the equation, the good old equation, Q equals mc delta T, or Q equals mcat. Remember that the m in this stands for the mass, not the number of moles. So, and Q is what you're trying to solve for. So, Q equals, we're going to use one of the 0.5 trials. So we're going to use 100.5 because that's the total mass of all the products and of all the reactants added together. You have 100 grams here and 0.5 grams there. So 100.5 times 4.18, which is the specific heat capacity of the calorimeter we're using. And we're going to use trial number 3, which is 28.1. Which should give you 1.72 times 10 to the 3rd joules for your Q. All right, that was pretty easy. Now we're going to go to problem number D here. And for problem D, we have to determine the student's experimental value of delta H for the reaction between MgO and hydrochloric acid in units of kilojoules per mole. Now this kilojoules per mole is really extremely important. So, from this, remember that negative delta Q equals delta H0. So, negative 1.72 times 10 to the 3rd joules equals delta H0. But that's just in kilojoule. That's just in joules. We need it in kilojoules per mole. So basically what you can do is eliminate this, and you have negative 1.72 kilojoules, right? Wrong. You have to make it kilojoules per mole. So in order to calculate this, you have to find how many moles of product is produced. And I think we calculated it was about 0.0125, right? When you divide that into that, you get about negative 136 kilojoules per mole, which is about negative 140 kilojoules per mole with sig figs. This answer is significantly different than this answer, so be sure you read what units they want it in. And now we have the last problem. Well, not the last problem. Problem number E. This uses another chart that you're given, but because this chart isn't important based on only what's written in the chart, I'm not going to copy it down again. So for this problem, we have to find the enthalpies of formation. You have to find the delta H using the enthalpies of formation. MgO has one of negative 602. H2O has one of negative 286. H plus has one of 0 because it's in its base state, and Mg2 plus has one of negative 467. So for this, you're going to want to use the combined heat capacities of the products minus the combined heat capacities of the reactants. So negative 467. Pardon me. Combined heat capacities of the reactants minus heat capacity of the products. Negative 602 minus 286. Minus 467. And that should give you negative 151 kilojoules per mole. Remember that only when you're using the enthalpies of formation do we use this formula. Now, you're going to want to, problem F. Okay, so in problem number F, it says that we're going to use the value calculated in number E as the actual value, so write that negative 151 kilojoules per mole down. And we're going to try and find out what gave the student his value calculated in problem number D, which is negative 140 kilojoules per mole. So in order to do that, it's asking if the calorimeter leaked heat into the environment, would it help account for the discrepancy between the values? And you have to explain for this. So this negative 140 kilojoules is pretty close to the negative 151 kilojoules. It's slightly less. If the calorimeter, which I'm going to draw up representing this triangle, leaked heat into the environment, this is calorimeter, then we would get a slightly lower delta H than if the calorimeter did not leak heat to the environment. So, yes, if the calorimeter leaked heat into the environment, it would explain the lower delta H because calculated delta H is lower than actual delta H. And a calorimeter leaking heat will lower delta H. And that is the last question in question number 3 of the 2013 AP exam. Now, before we finish this video, I'm going to tell you one thing that my chemistry teacher always told me, and that is to pay attention during your chemistry labs, because this is a lab practical question, and caught a lot of people off guard when we were taking the test. So, hit those books.